Okay guys, so in this video we're going to talk about section 8.3, which is about applications of integrals to physics and engineering. This section has two topics in it. One of them is about hydrostatic force and pressure, and the other one is about center of mass. So in this video I'm just going to talk about the first part. I'm just going to talk about hydrostatic force and pressure. And before we do any complicated problems, I just want to go through what does density mean, what does pressure mean, what does force mean, those kind of things. So let's get started. Okay, so first of all, density. Well, I'm sure a lot of you already know that density is mass over volume. The way you'd write that is density, the symbol is rho, we usually use is mass over volume. Basically what density tells you is it'll tell you the mass for a standard volume of something. So if we're talking about SI units, then the standard volume is a cubic meter. What a cubic meter means is, imagine the length of this line segment here is a meter. Then you build a cube out of this. Okay, so if that's 1 meter on the side there, 1 meter there, 1 meter tall, then the volume of this is 1 cubic meter. So if you can think of that as maybe it's filled with water, so then that'd be 1 cubic meter of water. And then what's the mass of it? Well, this rho tells you what it is. Actually, let me just tell you the density for water. For water, the density is 1,000 kilograms per cubic meter. This is for water. This section is about water only. That's what hydro means, hydrostatic, but hydro means water, so we're only going to be working on water. Technically, though, a lot of the stuff we're going to talk about in this section could be, we could talk about other fluids, other liquids besides water, but we're just only going to worry about water. Okay, so density of water is 1,000 kilograms per cubic meter. That means if you have 1 cubic meter of something filled with water, so for 1 cubic meter, its mass is going to be 1,000 kilograms. So for this thing, the mass is 1,000 kilograms. Okay, that means every cubic meter is 1,000 kilograms. So if you had some huge body of water, like for example, a swimming pool filled with water, let's say, or this is like a bowl, whatever, filled with water, and you want to know the mass of all the water in there, then you would just break it up into a bunch of cubic meters. Imagine that's 1 cubic meter right there of water. Here's another one. And in this way, you break up the whole pool into a bunch of cubes. And when you're done, let's say, for example, this was 80 cubic meters. That means there's 80 of these cubes in there. Well, each cube is one cubic meter. Okay, 1 cubic meter is 1,000 kilograms. So what if you have 80 cubic meters? Again, it's like you have 80 of these 1,000 kilograms. So the mass for this would be 80 times. You have 80 of these, so 80 times 1,000. So it would give you 80,000 kilograms. And in general, if you're trying to find the mass of, so if you have a liquid and you're trying to find how much mass it has, well, you can just use this formula and solve it for the mass. So if you solve that formula for the mass, you get mass equals density times the volume. Exactly what we just did. This is the volume, 80 cubic meters. Here's the density. You multiply them, and you get the mass. So that's the key thing that we're going to need here. So anytime you have, well, in this video, we're just looking at water. So if you have a bunch of water in a cup, in a pool, in the ocean, or anywhere, in a puddle, whatever it is, and you want to know the mass of the water, you just multiply the density times the volume, and the density is going to be 1,000 kilograms per cubic meter. Okay, so density of water, 1,000 kilograms per cubic meter, multiplied by the volume of the water, and you'll get the mass of the water. Okay, so that'll give you the mass. Now, that's if we're doing things in SI units, international system units, standard units, whatever you want to call it. But if you do this kind of problem in different units, in the English units. So I'm talking about like metric system units is SI units. If you do it in English system units instead, then instead of getting the mass of the water, you'll get the weight of the water. So let me just write what we had here. So density is mass over volume, which means the mass is the density times the volume, and the density of water is 1,000 kilograms per cubic meter. So again, the usefulness of what I've just written down over there is that if I have a volume of water and I want to find its mass, you just multiply the density times the volume, and the density is 1,000. So find the volume, multiply by 1,000, you get the mass. If you're doing things in English units, then we have a different symbol for density. It's going to be delta. And instead of it being mass over volume, it's going to be the weight of the water over the volume. And for water, and again, this formula can be used for any liquid, actually for solids as well, but we're going to be specifically focusing on water. So for water, the delta, the density for water, is 62.5 pounds per cubic feet. So this first one up here, if you're in the SI units, you're going to be ending up finding the mass of the water. If you're using this kind of density instead of the other kind, you're going to be finding the weight of the water. So this density right here is mass over volume. So that's like a mass density. This is weight over volume. So this is a weight density. Okay, and then you can get the weight of the object by multiplying by V, both sides. So you get weight is the density times the volume. And again, what does this mean? If instead of having 1 cubic meter, we had 1 cubic foot, so imagine this length now is 1 foot, and you built a cube out of it. Okay, then that's 1 cubic foot. So 1 foot here, 1 foot over here, 1 foot height. Then the volume is 1 cubic foot. And so if this thing is filled with water, then the weight of the water, not the mass, the weight this time is going to be 62.5 pounds. That's what this formula says. If you have 1 cubic foot, its weight is 62.5 pounds. And again, if you had a big body of water instead of just 1 cubic foot of water, so once again, you can imagine you have a pool, maybe I'll draw it like this time, and it's filled with water, and you want to figure out the weight of the water. Well, you break it up into cubic feet. So let's say that's 1 cubic foot, and you do this, and you just do this until you cover the entire body of water. I'm not going to do the whole thing. So there's another cubic foot, and so on. And let's say you end up with 40 cubic feet. Okay, so let's say the volume is equal to 40 cubic feet. In other words, it takes 40 cubes to fill up this pool, little tiny pool or whatever. Well, each cubic foot is 62.5 pounds. So each cubic foot of the water is 62.5 pounds. So if you have 40 of them, then you have 62.5 pounds 40 times. So that means the weight of the water, this W stands for weight, is, it's going to be 40 of the 62.5 pounds, which turns out to be 2,500 pounds. Okay, so in general, if you know the weight density of water and you multiply it by the volume of water that you're trying to talk about, then you can get the weight. Okay, so that's how that goes. Okay, let me just summarize everything I just said one more time. Just get rid of everything that's here. So if you're doing a problem and it's in SI units, you're going to know if it's in SI units if you see meters or if you see kilograms. So if it's in SI units, then the density of water, the mass density, is 1,000 kilograms per cubic meter. And since density is mass over volume, This gives us that the mass is equal to the density times the volume. So trying to find the mass of some amount of water, you just do 1,000, because the density is 1,000, times whatever the volume of water is. Okay, so any problem, if you know how much volume the water has, and the volume is in cubic meters, then you multiply by 1,000, you get the mass of the thing, and your mass will be in kilograms. Now, so for the English unit version, delta, which is the weight density of water, it's 62.5 pounds per cubic foot. So the formula for delta is the weight of the water divided by the volume. So if you want to know the weight of the water, you multiply the delta by the volume. And so what that means is if you have an amount of water and you want to know its weight, well, you just take the delta, which is 62.5 pounds, and multiply by the volume of the water, and you'll get the weight of the water. For this problem, this kind of problem, the volume needs to be in cubic feet, and then the weight will be in pounds. Okay, a couple quick examples. Okay, example 1. What is the mass of a 0.54 cubic meters of water? So 0.54 cubic meters of water is like, a large bucket of water. Okay, and if I have a large bucket of water, what's the mass of that thing? So I'm giving you the volume. This is volume, cubic meters. It's how much water we have. And I want to find the mass. So the way we're going to do it is the mass. Remember, the mass is the density times the volume. We're talking about the mass density. So that gives us the mass is equal to 1,000 times the volume, 0.54. And so just do 1,000 times 0.54, you get 540, and the units are going to be kilograms. Notice this was in the correct units for volume, SI units for volume, cubic meters. So my mass answer is going to be in the correct SI units for mass, 540 kilograms. So that's the mass of the water. Okay, example 2 is basically the same question, except it's in English units. So I'm giving you the volume of water again, but I'm giving it to you in cubic feet. So I'm saying you have 2.78 cubic feet of water. Again, I'm trying to tell you how much water you have, the volume of the water. And you're going to tell me the weight. Oh, I'm missing a T over here. Okay, weight. Okay, of the water. But since I want the weight, you're going to do the same thing. You're just going to use the other formula. So the other formula said that the weight of the water is the delta times the volume, the weight density times the volume. Okay, so you're going to get the weight instead of the mass this time. So you do weight is delta, which is 62.5 times the 2.78. Okay, so 62.5 times 2.78, and you get 173.75. And what are the units going to be? Well, if this is in English units for volume, which is cubic feet, then the weight will be in pounds, the English unit for weight, pounds. That's how much the water will weigh. Okay. On to the next thing. Pressure. Actually, before I talk about hydrostatic pressure, so pressure in water, let me just give you a quick idea of what pressure means, or just one quick example. So imagine for a second that the ground, imagine, there's dirt on the ground and it rained. So imagine this is the ground here, okay? And the ground is wet but not muddy, so it's like solid ground, but it's not muddy. If you walk on it with your shoes, say this is your leg here and these are your shoes, okay, and you're walking along it, okay, so you walk along it. Well, if it was real muddy, I understand you'd push down into the dirt, you'd make a big print and maybe slip or whatever. But if it's just a little bit wet and you walk on it, you will barely push it down, just a little bit. There'll be a footprint, maybe. I mean, a shoe print, whatever it is. But it would go inside the ground, maybe just slightly, just little imprint right here. That's me trying to draw an imprint when your foot will go down into the dirt a little bit. Now imagine instead that you're wearing cleats. Okay, so let me draw the imprint again real quick. So maybe your foot went down that much and you put a little imprint of your foot into the dirt. If you're wearing cleats instead, see, the thing is, the area under your shoe is kind of big. But if you're wearing cleats, in other words, that means that you have a bunch of little spokes on the bottom, and the area under the spokes is much smaller. So what'll happen is when you walk on that kind of dirt with spokes, you're applying the same force because it's your weight that's pushing down. But even though you're applying the same force, the area that's touching the ground is much less. So because pressure is force divided by area, that's the main formula for it. You're applying the same force but less area. And if you make this less, the denominator less, you make the pressure more. So when you're walking with cleats, you put a higher pressure. So when you walk on cleats, so imagine this is your foot again. These are your cleats going into the ground. Something like that. So the cleats will go into the ground. You will be able to now make a big hole in the ground. You'll put, not a big hole, but a deep hole. You'll push deep into the ground because you're applying more pressure. And again, why more pressure? Because the area here is, it's hard to see, but it's the area over there. Whereas here you just have less area total pushing down on the ground, but the same weight, same force. So that gives you some kind of idea of what pressure means. Pressure is force divided by area. So in other words, bigger force is bigger pressure, but smaller area is also bigger pressure. So in this case, we're pushing down same force, but smaller area. So we apply more pressure, and that's why the cleats go all the way into the ground. Whereas if you just have a flat bottom on your shoe, you're applying same force, but a bigger area. So it's not going to put as much of an imprint in the ground. It's not like your whole foot goes into the ground. Whereas in this case, the whole cleat does go into the ground. Once the cleats are in the ground, then the rest of your shoe now has much more area, so that part doesn't go into the ground that much. Okay. So that's just one quick story I want to tell you. And now, okay, pressure, as far as water goes, the deeper you go into the water, the more pressure you feel. Why? So in this picture here, we have a flat plate. Imagine this is like a plate laid flat, like you put it on the surface of the water like it's floating, and then you push it down. So in other words, I'm trying to say that if this is the surface, it's parallel to the surface. It's not like slanted or anything, but they drew it kind of slanted so you can see it, but it's flat. In other words, every point on this plate is the same depth, same distance below the ground, every point. Okay, so because this plate is submerged in the water, it's going to feel a force. Why is it going to feel a force? Because there's water above it. So it's kind of like, if you put a backpack on, you feel a force on your back because you have this thing on your back. Same kind of thing here. This plate has water on its back, so to speak. So how much water does it have on its back? Well, if I draw a line from here up to the surface, a line from here up to the surface, those lines have the same distance, by the way, because they're the same depth. I know they don't look the same length, but they're the same depth. Same thing over here. If I draw a line up to there and from here up to there, we get this sort of shape. And all the water in there, that's the water that's above the plate. So that plate is filling a weight. What weight? The weight of the water above it. So let's do things in SI units first. In like metric system kind of units. So I want to find the volume of the water. Then I'll find the mass of the water. Then we'll find the weight of the water. Okay, so the volume of the water. Well, anytime you have a cylinder like this is a cylinder. Okay, for example, what is a cylinder? Here's an example of a cylinder. Circle, circle, and on the sides, vertical line. So that's a cylinder. That's the kind of cylinder you're probably used to seeing. But a cylinder is any area at all. So it could be, a triangle instead on the bottom, triangle instead on top, and then straight sides. That shape is also a cylinder. This is called a right circular cylinder. I don't know, you might call this a right triangular cylinder or something. I don't know. Whatever the shape is. So in this case, we have some kind of plate shape. And we have the same kind of plate on top. And then straight lines like this. So that's still a cylinder. And anytime you're trying to find the volume of a cylinder, it's always the area of the top times whatever the height is. Okay, so volume is area of the top times the height. Over here, same thing, whatever the area of the top is, times the height. Here, area of the top, whatever it is, times the height. That's always the volume of a cylinder. So in this picture here, it's the area of the top, which is the area of the plate, times how high it is. In this case, they called the height D, or D for depth, I guess. How much below the surface of the water is this plate? So that's the volume of the water that's on top of this plate. Okay, so then we can find the mass, because the mass from the last slide was density times the volume. So it's the density of water times, then the volume is A times D. So that's the mass. Okay, next thing I want to do is I want to find the weight of the water. If you know the mass of something, you can find the weight on Earth anyway by multiplying by G, by multiplying by 9.8. If this was on the moon or something, of course, you'd multiply by something else. But on Earth, so everything we're doing is water related and on Earth. Okay, so you multiply by G. So the weight of the water that's above this plate, so the weight of this water here is, well, it's mass times G. That's the formula for weight. It's always mass times G, where G is 9.8. And the mass we just found was rho AD. So it's rho AD times G. Okay, so that's the weight of the water, which is the same thing as the force on the plate. So maybe I can just call this force now. So the force on the plate is rho AdG. That's the force on the plate. Now, the bigger the plate, the bigger the force. It makes sense because you have twice the area, you got twice the amount of water, you got twice the force. So what we want to do is we want to standardize that, and we're going to standardize it with pressure. Pressure is going to tell me the force on 1 square meter of whatever you're putting down there. So what's the force for 1 square meter? And then if you want to find the force for any other size besides that, you're going to multiply. So that gives us the formula for pressure. Remember we said it was force over area. So the pressure, the force we just found, rho AdG over the area. And the A's cancel and you get rho dG. So that's the formula for the pressure on the plate. And again, what does the pressure mean? It's the same thing as the force if the plate was 1 square meter. And if it was more than 1 square meter, you just multiply by the area to get the force. So in SI units, the pressure is rho dG. Remember, rho is just 1,000, G is 9.8, and D is the depth. And if you want to get the force on the plate, if it was exactly 1 cubic meter, 1 square meter, the plate, then you could just multiply, then you could just say the pressure is the same as the force. But if it's any other area, then the force on the plate is going to be, it's like I'm taking this thing and solving for area. Solving for force. So it's the pressure times the area, which would be rho dG times the area. Okay, so that's the formula for the pressure. That's the formula for the force on the plate. Okay, and that's of course if we're doing things in SI units. And that would mean that pressure would be in pascals. That's the SI units for pressure. And force would be in newtons. Okay, so the units are for pressure is pascals, the SI units. PA, it's short for pascals. And then the force will be in newtons. So you'll just write N, which is short for newtons, like that. Okay, before we talk about the English system way of doing things, I just want to talk about the direction of the force real quick. Well, what's the direction of this force? So since there's this water above the plate, it's like the water is pushing down on the plate. So the force can be thought of as acting down, pushing on the plate downward like that. Experimental evidence says that there's other forces as well on the plate besides the downward force. Just because of the fact that it's in the water, there's also an upward force, same magnitude, on the plate. So that's a little confusing. We derived the formula from thinking about this weight of the force above the plate, of the water above the plate, and the weight of the water is pushing down. But then now we have to get this idea that comes from experimental evidence that says that there's going to be a force in all sorts of directions, and let me talk about how that's going to go. But there's a force upward as well, and you're going to say, well, I don't see in the picture where that force upward is. And all I could say is, because the pressure is the same at depends on the depth, and there's going to be forces in other directions as well. Force is always going to be perpendicular to the area, and because we have water above it touching the plate, it's going to push downward. Since we have water below the plate, it's going to push upward. So basically, wherever the water is touching, it's like the water is going to be pushing. So if the water touches the plate, it's going to be pushing in that direction. So that part we're just going to have to believe without getting a real clear idea of why that is. Let me draw another situation so we can talk about directions of the force. Let's say I put another plate, but it's sideways. So this is now, the plate's like this. I'm going to make it thin. Okay, but this area here is the whole area of the plate right there. That's it. So what direction is the force on this plate? Well, it's got water touching it on both ends, so there's going to be an inward force. I guess I can't really draw that, so I'm going to draw it like this. There'll be a force pushing in from the water that's on top of the, well, not on top of the plate, but in front of the plate, and there'll be a force like this due to the water behind the plate. So behind the plate, water is pushing this way on the plate, and the water that's on this side of the plate is pushing that way on the plate. So wherever the plate is, perpendicular to the plate, we got forces in both directions. Now the reason I drew a thin plate here is because if I would have drawn a thicker one, so let's say a plate is like this. Now the force is not constant because the force depends on the depth. You see, force depends on the depth. So up here, there's a force on this part of the plate, this part, but down here, there's a force on this part, and it's a bigger force because we have a bigger depth. So that's why we need calculus to do things like this. So if we submerge a plate like this in the water, so instead of it being flat, imagine you put a plate perpendicular to the water and then you push it down. So we have this plate like this. Well, this part has a certain force, this part has a bigger force, then a bigger force, and a bigger force. And that's why we need to use calculus, because we're going to need to approximate each of those forces, because none of them are at one single depth. See, if the plate is perpendicular to the surface like this, they're all at the same depth, then we have no problem. The depth is the same. But when you put it this way, the plate this way, then different points are at different depths, so they have different forces on them. Okay, so let's go ahead and look at the English way of doing things. What's going to be different? Well, still the weight of the water is going to create this force. Okay, so in the English system of units, well, what's the weight of the water? Earlier we found the weight of the water by finding the volume, then the mass, then the weight. We're going to do the same thing, but we're just going to go from the volume straight to the weight because we're going to be using delta. So the volume, just like we said before, the volume is going to be the area times d. And then since we have this delta density, the weight density, we know the weight of the water is delta times the volume. So you don't have g anywhere because we're not going from volume to mass to weight. We're going straight from volume to weight. Okay, so this formula here gets me from volume to weight, so it's going to be delta times AD. That's the weight of the water. And so then the pressure, since it's force over area, remember this is also the same as the force that the water above the plate is pushing on the plate with. So it's going to be delta AD over A. The A's cancel, you get delta D. And so we have these formulas. So the formula for the pressure is delta D. So we have two formulas for pressure. Rho dg if you're in SI units, or just delta D if you're in English units. Remember, delta is the 62.5. And then the force on the plate, remember that's just the pressure times the area, or we can just write delta AD. We have it over here already. So delta AD. And if you're in the English units, then the English units for pressure, I think we'll just have to call the units for pressure pound per square foot. That's not a standard unit, but if we're using feet for English units, then and pounds for our force, then that's what that would be in. This would be in pounds here. Even though the more common unit for pressure for English units is pounds per square inch. We might have to do some unit conversions to get that, but PSI, which is the same thing as pounds per square inch. Okay, so that's a more common one. But anyway, so we have these formulas here. All right, let's go ahead and practice this with a couple of examples. So what is the pressure at a depth of 3 meters below the surface of body of water? When I ask you for the pressure, you don't have to tell me what you're putting in the water. But if you tell me what you're putting in, then I can figure out the force on that thing. But otherwise, I could just say, what's the pressure at this depth? So anything at that depth has the same pressure on it. So what's the pressure at a depth of 3 meters? Okay, well, the formula for pressure was rho dg. So it's 1,000 times 3 times 9.8. 9.8 times 3 times 1,000. And I'm getting 29,400, and the units are pascals. This is all in SI units. Okay, so we have meters here, and the other quantities are in the correct SI units, so we get pascals for that. Okay, and then it says find the force. So find the hydrostatic force on something if you put it 3 meters deep. So the pressure is going to be 3 meters, but now here is the area that we're putting in. And again, I have to assume that this area is this thing that's being put in is submerged parallel to the surface of the water. So if this is the surface of the water, the object is parallel to it. Let me try to draw something parallel, and we submerge it in. So when it's down here, it's parallel to it. And when I say parallel, I mean every point on this object has the same depth below the water. Okay, because again, if it's submerged this way, where these points are closer to the surface and these points are further away from the surface, then it takes calculus to figure out that, which is what we're going to be doing in a few minutes. Okay, so anyway, to find the force, you just multiply the pressure times the area. Remember, force is pressure times area. So you can use this formula, force equals pressure times area, or you can use the formula force equals rho AdG, the way we had it on the other slide there. So either way, let me go ahead and just use the bottom one. If you use the top one, the pressure you're going to put is this. Otherwise, you just, from the numbers they gave you, use the bottom one. So it's 1,000. The area they're giving you is 2.1 square meters. That's this. Depth is 3. 9.8 for G. Let's see, multiply those. And you get 61740, and the force units is newtons. Okay, so that example there, part A and B, were about things in the SI units. Let's go ahead and do a problem in English units. Now this says, what is the pressure at a depth of 8 feet below the surface of a body of water? So see, it says 8 feet, that's English units. To find the pressure, it's just delta D. So 62.5 times the 8. Then you get 500, but again, it's in weird units. It's pounds per square foot. If you wanted to get it in PSI, which is a more standard unit for pressure, you'd have to multiply by, let's see. So we want to get rid of the square feet and we want to have square inches. So you're going to write 1 foot is 12 inches and you multiply by that twice. So that way the top says square feet. These square feet will cancel at the bottom and we'll get square inches. Basically, you're going to divide by 12 twice. And you're going to get 3.47, I'm rounding a little bit, 3.47 PSI. Okay, so 500 pounds per square foot. If the online homework takes that, great. Otherwise, if they want PSI, you're going to go ahead and put this. So that's PSI, pounds per square inch. Okay, now, even though this is a more standard unit for pressure, what we're really going to want to find in this section is the force. So to find the force, we're going to want the pressure in this form, because then we're going to multiply by the area with standard areas in square feet, and it'll give you the weight of the thing. So this one says, part B says, what is the hydrostatic force on an object of area 5.1 square feet if it's submerged at a depth of 8 feet below the surface of the body of water? Once again, that this object is, so that's the surface of the water, surface. We're submerging it in such a way that every point on the thing has the same depth. All these things, all these depths are the same. D, D, they're all D. Because otherwise, if the depths change, then that's where we're going to need calculus to do it. So that's what we're assuming in this problem. Okay, so how do you find the force? Again, there's two ways. One, you could do pressure times area. You could use this pressure here and multiply by the area and be done. Or you could use the other formula that's delta AD. So either one of those. Let me go ahead and use just the second one, but it doesn't really matter. So delta AD, so 62.5 times the area 5.1 times the D, which is 8. And let's see. I'm getting 2,550 pounds. So anyway, as far as the pressure being weird units, doing pounds per square foot, I don't think finding the pressure is going to be that important, because what we really want to do is we want to find the hydrostatic force. Okay, so again, if they ask you in the homework for hydrostatic pressure and they want it in PSI, this is what you have to do. You have to multiply by 1/12 a couple of times, but otherwise, if they don't mind it being in pounds per square foot, then you just do that. Okay, one quick note on x coordinates and distances. So if you have an x-axis or y-axis or whatever, so here's an axis. Let's say this is the origin right here, so this is 0, and you have a point over here. So if I call the x-coordinate x, well, since I'm putting it on the right side of the origin, x is positive. So when the x-coordinate is positive, then so that's telling you the number on the number line here. Okay, so if this x is 5, then the number on the number line here is 5. But it's also telling you the distance from the origin to here is 5, so in this case x. So x coordinates and distances are not always the same, but if the x coordinate is positive, then the distance from the origin to the x-axis is also that x. Okay, so just share a quick example here. If I have the origin here and this is the number 3, so 3 is the number here, but 3 is also the distance here. Okay, and in general, if I call this, like, we have 0, and let's say later on in a problem we have like xi star right here. I'm trying to say that's the x coordinate of this point. That's the number that you see on the number line there. But since it's on the right side of the origin, it's a positive number, and the distance between 0 and here will also be xi star. So so that'll be a distance, and it'll also be the number on the x-axis there. It's one little thing I wanted to mention because we'll see that show up when we do problems. And this slide just summarizes all the formulas that we talked about in this video so far. This is just the formula for pressure. This is always true. And this is the formula for weight. If you know the mass, weight of something is mass times g. But the formulas we're going to need when we're doing problems, if we're doing problems in SI units, we need these 3 formulas. This is the formula for the density. And if you want to know the pressure, here's the formula for the pressure. And here's the formula for the hydrostatic force. If your object's at a constant depth d, the depth doesn't change, it's constant. So the entire object is at the same depth, and there's the force there. And the 2 examples we're going to do, they're going to ask us for hydrostatic force. So that's, we're going to be worrying about the fact, is the depth constant or not? If we're doing things in the English units, then here's the formula for density. It's weight density. This was mass density. This is weight density. And this is the formula for the pressure, hydrostatic pressure, at a depth d, and here's the formula for hydrostatic force at a depth d. And again, for both of these formulas, so all these formulas, basically, the depth has to be constant. So you submerge something that has an area, but the depth is constant. Every point on the object has the same depth below the surface of the water. All right, let's do some examples. All right, a dam has the shape of a trapezoid. The height is 20 meters and the width is 50 meters at the top and 30 meters at the bottom. Find the force due to hydrostatic pressure on the dam, they mean, if the water is 4 meters from the top of the dam. Okay, so it's possible what they're drawing here is a little bit unclear. So let's see what's going on here. Okay, so in this picture, they're showing you're seeing water, but here's what's going on. So I'm going to show you a couple of different views, first of all, of what's going on. So a dam is a wall, and so there's a wall. We'll say this is like a side view of the wall. And then there's this water here. Okay. And this wall is there, the dam. It's just there so that it's not letting the water pass the dam. That's the idea there. Okay, that's a side view. Now, if you look at it from this end, this is an eye looking at it from this end, then you would get a picture that looks like this. So the wall is a trapezoid. And if you could see through this wall, if you could see through it, then you can see that there'd be water up to this level like this. So the water's not all the way to the top. There's some space there. You can see the space over here. Like that's how much that part of the wall is not being touched by water. And that part of the wall that I circled over here, if we're looking at the wall from the side, if you look at it from this end, that's the part of the wall that's not being touched by water. Okay, so that's the first thing that's going on. The next thing that's going on is, so we're going to be using this picture here, and just think of it right now as that this black outlined thing is the wall, and it's see-through, so you can see the water behind it, the water that it's holding back. What's going to happen is we're going to have to cut the dam, at least the portion of the dam that has water behind it, into pieces. We're going to chop it up into a bunch of rectangles. We're going to use the rectangle approximations. So these rectangles are supposed to approximate the dam. And then the reason, first of all, okay, a couple things. Why am I drawing rectangles this way? Well, I only drew, how many did I draw here? I drew 6 in the picture there, but can you imagine instead of 6 rectangles, there was like 1,000,000 rectangles? If you saw 1,000,000 rectangles, then let's focus on one for a second. Let's say this is one. Let me change the color. So let's just do green here real quick. So if this is just one of those rectangles right here, okay. So you understand the rectangle has a top and a bottom. There's a top of that rectangle and the bottom of that rectangle. Actually, make it in black. I mean, it's a little hard to see in green. Okay, there it is. Okay, so we have this one rectangle here. The thing is, if you draw rectangle horizontally like I've done, and if we've drawn millions of rectangles, like 1,000,000 rectangles, then the top and bottom are very close together. Imagine 1,000,000 rectangles. They're so close together that the depth of the top of the rectangle and the depth of the bottom of the rectangle are about the same. I know in this picture it doesn't look like they're the same, but that's because I only drew 6 rectangles. And what do I mean by depth? I mean how far down from the surface of the water is the top of the rectangle? How far down from the surface of the water is the bottom of the rectangle? Again, if it's a very, very thin rectangle, then you can't really tell the difference between the top and the bottom. And so we can approximate, we can say that the whole rectangle is approximately at the same depth if you cut it horizontally. If you were to cut it vertically, then no matter how many rectangles you use, the depth of this part and the depth of this part are going to be way different. But if you cut this way, and again, let me maybe draw one over here. Imagine super thin rectangle here like this. That's still kind of thick, but anyway, you get the idea that the top and bottom have almost the same depth. So we can pretend the depth is constant throughout that one rectangle. And since the depth is constant, we could figure out what the force on it is. Okay, third thing is, imagine we chopped it into 6 rectangles like we have over there, but let me go ahead and draw it on the picture on the bottom here. So let's say this is a side view of those 6 rectangles. Okay, so there's a side view of those 6 rectangles here. So this rectangle over here, the dam, because there's water behind it, the dam is getting a force applied to it in this direction here. Remember, the hydrostatic force is going to be perpendicular to the dam in the direction as if the dam is trying to push on the wall. The next rectangle below it will have a larger force on it. Remember, force is a vector, so I'm just showing you the direction as well. There's a larger force on it. So this is the force on that rectangle. Here's a force on the next rectangle. And they're going to get larger as we go, lower. But they're going to get larger because the force has the depth in there. So the deeper it is, the more force is being applied on it. So we have all these force vectors, okay? And basically the idea is we want to add up all these force vectors. The good news is they're all in the same direction. When you add vectors, the rule is you add them tail to tail. So if I drew all these vectors tail to tail, like this first one, and then the second one, and then the third one, and anyway, on and on we go, 5th one, 6th one. When you add vectors and they're all already pointing in the same direction, you draw them head to tail to see what the resulting vectors. It's going to be one long vector in the same direction again. And all you do is you just add the length of the individual ones to get the length of the answer. So basically what we're going to do is we're going to find just the length of each of these force vectors and add them up, and that'll give us the length of the resulting force vector. And we already know the direction of the force vector is going to be, the water is touching the dam. It's like a hand touching a wall, and we're like pushing directly on the wall. That's the idea. Okay. So we do have to chop this dam into a lot of pieces. But what I'm going to do first, just to make it a little bit easier to understand, is I'm going to chop the dam up into 3 pieces, 3 rectangles. The idea is, of course, we're going to use more and more rectangles. That means we're going to let the limit as n goes. We're going to have n go to infinity, where n will stand for the number of rectangles we use. And as we use more and more rectangles, the 2 approximations that we're going to make right now are going to get better and better. So just for the moment, let me go ahead and chop this dam into 3 rectangles. That means I'm going to draw some kind of line around here somewhere and around here somewhere. I'll go ahead and finish it. Actually, before we chop it, let me mention one more thing before we chop it. So every time you do a problem like this, you need to draw an x-axis. There's a lot of different places you can put the x-axis that'll all work. But what I'm going to do is I'm going to draw an x-axis that goes downward, vertically downward, like that. So that's the x-axis. And I'm going to put the origin, the 0, right here, where at the top of where the water is. You can put it other places too. You can put the origin here if you wanted, or you could put it here if you wanted. You can make the x-axis point up if you wanted. But I think if you point it up and you put the origin in a bad place, you might have some negative numbers, and I kind of don't want to deal with any negative numbers. So let's put the origin where we have it and the line where the direction is going. But again, this is not the only way to do it. Okay, so now what we're going to do is we're going to cut the segment, the line segment from here to here, where the water is. We're going to cut it into 3 segments. Okay? So put a tick mark here, a tick mark here, and a tick mark here. And that's going to give us 3 rectangles. So when I draw the rectangles, I'm going to draw them sideways. How far should I go? So I want to draw a rectangle that goes like that. I want to go this way, and same thing here, go this way and this way. But I have to decide how far to go. So what I'm going to do is I'm going to go, because this end you'll see will be a little shorter Then the top end, I'm going to go a little bit past the dam here. And here I'm going to go a little bit before the dam and draw a rectangle like that. So a little before the edge of the dam, draw a rectangle like that. Or you could think of it as I'm using the midpoint here to give me how far to go on both ends. So I'm going to use the midpoint. You don't have to use the midpoint. You can use any point in the middle, but I'm going to draw it as if I'm using the midpoint. Okay, then for the next rectangle, I'm going to draw the same thing. This end here is going to be shorter than the other ones. I'm going to go a little bit past the dam right here, here and here. And we'll go a little bit before the dam, and we'll go like that. So I want you to notice that as far as this rectangle goes, sorry, I went too far on this side here. Just a little bit past and up like this. So again, I'm trying to make the rectangle not touch the dam on either end. So this end is not exactly touching the dam, and this end is not exactly touching the dam, but some point in the middle it's touching the dam. Same thing on this end. This end is not touching the dam, and neither is this end, but some point in the middle is touching the dam. Let me try to erase those. Okay, so we'll draw a third one again, going down here. I'm going to go a little past and go up. Here we'll go a little bit past and go up. So you agree that the area of those three rectangles is not the area of the trapezoid. Actually, if you use the midpoint, it actually would be equal to the trapezoid, but in general, you see that we're missing some parts, like this area is not covered. And then you can see like over here, we have some area that should not be covered. So it's an approximation, but the idea is the more and more rectangles you use, the closer and closer the areas of the rectangles will get. If you add all the areas of all the rectangles, the closer that area will be to the actual area of the trapezoid. So that's the first thing. So basically, a whole bunch of rectangles. If I have a million rectangles, you won't be able to tell the difference between the collection of the million rectangles or the trapezoid. They'll be very close to the same. Okay, and now the next thing is that we want to find the force on each of these rectangles and add them up. So it's going to be 3 forces we're going to be looking for. Let me get rid of these dotted lines here. Okay, I'm going to put the origin back here, but I'll put it in black this time. And then this number over here is 30. No, it's not. What is the number on the other end over there? So we know that the height of this whole thing is 20. But the problem also says that this distance from the water to the top of the dam is 4 meters. So that means the distance between the top of the water and the bottom of the water is 16 meters. So if this is 0 up on top, then this number down here is 16. Okay, 16 is the bottom there. Okay. And now I'm going to label where each of these tick marks are. So the first one, we're going to call it x0. That's also called A. This tick mark is at x1. This tick mark is at x2. And the 16 is at x3, which is also called B. Okay, now I'm going to label points in between. We're going to end up with a Riemann sum. When you have a Riemann sum, you need to be plugging in a number in between each interval. And what I'll do is I'll label it as if it's the midpoint, but it doesn't have to be the midpoint. So the point in the middle here, I'll call that x1 star. x1 because it's the first rectangle. This point over here in the middle, x2 star. This point over here, x3 star. If you want to call it the midpoint, you can do that. Otherwise, some point in the middle. Okay, and now what I'm going to do is I'm going to figure out the force on each of these rectangles and add them up. We're going to have a second approximation here. I'm going to pretend that each rectangle's width is very small. In other words, the depth of the top of the rectangle the depth of the bottom of the rectangle. The depth of any point on a single rectangle is about the same. So, okay. Let's find the hydrostatic force from the first rectangle. Well, this problem is in SI units, so the force formula, I mean, there's a few ways to do it, but we can just go straight to the force formula. It was rho dg times A or something like that. Okay, where rho is the density of the water, that's 1,000, d is the depth, g is 9.8. So don't worry about rho and g, those are just numbers. The d is the depth of the rectangle, and A is the area of the rectangle. Okay, so let me just call the area of the rectangle A1 for now. And then what's the depth? Well, the depth is going to be, you could call it x0. That would be the depth of this point. You can call it x1, would be the depth of the bottom end of the rectangle. Or you can call it x1 star, which is the depth of the middle one. We'll just use x1 star, but remember x0, x1, and x1 star, they're all about the same if we'll be able to draw on 1,000,000 rectangles. So that's the idea. When you let n go to infinity, you draw 1,000,000 rectangles, then the approximation gets better. So the force is rho x1 g a1. Well, you could do this for each one. The force on the second rectangle is going to be rho, I'm going to put the g first, rho g, and then the depth would be x2, sorry, I meant to put x1 star here. So x2 star here, and area of rectangle 2. The force on the third rectangle would be rho g x3 star a3, and you'd add all these up. So the total force would be sum I equal 1 to 3 of rho g xi star ai. That would be the total force, but it's an approximation. The total force, if we assume that this is a good approximation, so that'd be the idea there. Okay, so now what I'm going to do, we still have to find the area, but what I'm going to do is, so I don't have to do too many calculations, we'll just do one. So I just drew this picture where we chopped it into 3 rectangles, but now I need you to imagine, instead of chopping into 3 rectangles, we've chopped it into millions of rectangles. Okay, so we get a better approximation for the total force. So I'm going to be doing some erasing here. Let's get rid of the rectangles that I have. And since it's 1,000,000 rectangles, I don't want to draw all 1,000,000 rectangles. So I'm just going to draw one of them in the middle. But then we'll get the idea how it works for all the other rectangles all at once. Okay. So I'm going to draw this rectangle somewhat big, just so we could see it. But you need to imagine it's very, very thin. Okay, so I drew this one, the 2 tick marks super far apart, but I need you to imagine they're super close together. Still, though, you would draw the rectangle, you would go here to the dam and go a little bit past it. What you're doing is just drawing a rectangle somehow. And you get this rectangle here. And if this is like the 100th rectangle, then this number would be x sub 99. This would be x 100. But instead of me calling this the 100th rectangle, I'm going to say this is the ith rectangle. So I is going to stand for which rectangle it is. So if I is 1,000, it's the 1,000th rectangle. And that would mean that this number here is xi, and this number here on the x-axis is xi minus 1. In other words, 1 less. The subscript is 1 less than the bottom one. So xi for that tick mark, xi minus 1 for that one, and some point in the middle, we'll call it xi star. So I just want to find the force, the hydrostatic force, the force of the water on that part of the dam, that one rectangular part of the dam. Okay, so let's get rid of this. It's basically the same idea. I'm just finding one of them right now, and then we'll add them all up because we have to do it for all the rectangles. So that's the idea when you do a problem like this. You just draw one rectangle, and you get the answer, and then you say, well, it's the same kind of answer for any rectangle we have. We just change the I. So the force on this ith rectangle is rho g dA. Remember, rho and g are just numbers. D is the depth. The depth is going to be xi star. And A is the area of this rectangle. So that's our job now. We've got to figure out the area of this rectangle. And it's going to have an I in it. Okay, so I think that's the hard part of the problem, just figuring out, what's the area of the rectangle. Well, it's a rectangle. So the area of a rectangle is length times width, or base times height. This distance here is the distance between the tick marks, and that distance we call delta x. Sorry, that's a little unclear. I'll put it over here. So this distance right here, delta x. Okay, so then I just need to figure out what the length of, we can call that the width of the rectangle. I have to find the length of the rectangle. And the way we're going to find the length of the rectangle is we're going to chop it up. So I'm going to draw a line like this. I'm going to draw a line like this. I'm looking for the distance between here and here. That distance right there is what I'm trying to find. That would be the length of the rectangle. But for now, the length of this part of the rectangle, this yellow line that I'm drawing, just that much. That's not the length of the entire rectangle, but that's the length of part of it. What is that? Well, that's 30. You see down here, from here to here, it's 30, right? 30. That means if you just look from here to here, that's 15. And then the distance from here to here, this distance, we're going to have to figure that out. I'm going to call that distance A. So when we're done, the area is going to be 30 plus 2A times delta x. The delta x is the width, and the length we already saw was 30 from here to here. Then there's an A right here, and there's another A on this side. Okay, so A, 30, and another A. So the width is 30 plus 2A. And our job is just to figure out what this A is, and we can figure out what the A is, then we'll be done. Okay, too much stuff going onto my picture now, so let's erase some stuff. Okay. Now, in order to get A, we're going to have to use similar triangles. So how are we going to do that? So we have this triangle here that I'll draw in purple. Okay, so this one, like this, and like that. Okay, so we have this little purple triangle. And then we have this other one I'll draw in yellow. So it's like this, and like this, and like this. Those two triangles are similar. Okay, now what do I know about the yellow one? Well, I know that the length of this side here, the left side of it, is 20. Because it goes from the bottom here all the way up to the top of the dam, past the water. It goes past the water, the triangle I've drawn. So that length is 20. So I'm going to put a 20 there for that length. How about the length on top? Well, you know that this distance is 30 from here to here. And so that means the distance from here, sorry, this yellow is not cutting it on the white. Let's try a different color. Green sounds like a winner. Let's go from here to here. This distance is 30 because it's the same as this distance. So then you can figure out what this distance is and this distance. They have to be the same because it's like a mirror image, and the total has to be 50. So if the distance from here to here is 30, that much, then this has to be 10, so that we have another 10 there, and then we have 50 total. So as far as the yellow rectangle goes, the top distance is 10. Okay, as far as the purple rectangle, let me try to draw the purple rectangle in there again. So there's the purple one more time. It goes from here to here, there to there, there to there. We know the top side is A. And the length of the left side of it, well, how are we going to get the length of the left side of it? Well, I know the distance from here to here is xi star. But I want the distance, I'll go ahead and draw it in green, from here to here. That green distance. Well, this green distance here, if you add it to this purple distance here, you're going to get 16, because that's just the height of the water. The water goes from here to here. With that distance was 16. We figured that out earlier. Don't forget the distance from this spot to this spot is 20. From these two dots is 20. But the distance here of where there's no water was 4. That was given in the problem. So one more time. The distance from here to here then is 16. So 16, and the purple distance here is xi star, because that's the x-coordinate of this point, and I mentioned x-coordinate of that point is the same as the distance over here, xi star. So the distance that I want, the distance for the left side of the purple triangle, is going to be 16 minus xi star. 16 minus xi star. That's the distance for the purple rectangle. Okay. So there's a little bit of stuff to figure out there. But now let's go ahead and use similar triangles and see what we get. So similar triangles. Okay, so if you do the top of the yellow divided by the top of the purple, you can get the same answer. Okay, realize that I used the yellow on top. So now for this next fraction, I'm going to use the yellow on top. So top of the yellow divided by top of the purple. Now here I'm going to do the left of the yellow divided by the left of the purple. The left of the yellow was 20. And the left of the purple one was 16 minus xi star. I'll just write it over here, minus xi star. All right, so similar triangles gave us this result here. And so now you got to solve this for A. So what you can do is you can cross multiply, and you get 10 times 16 minus xi star equals 20A. And if you divide both sides, so you could do a lot of things here. You could distribute to 10. You could divide both sides by 10. You could divide both sides by 20. You might want to divide both sides by 20 to get A by itself. But here's the deal. If you look at what I need, I actually need 2A. So I'm just going to divide both sides by 10. Because if I divide both sides by 10, I'll get 2A. Just trying to save a little bit of work here. So we get 16 minus xi star is equal to 2A. So over here, we're going to put 16 minus xi star in place of the 2A. All right, so the hydrostatic force on that rectangle is rho g xi star, and it's 30 plus 16 minus xi star delta x. Okay, if that made sense, let's clean it up a little bit. Okay, so we have rho g xi star. And then inside is 30 plus 16 is 46. We have 46 minus xi star delta x. That's the force on just the one rectangle, the red rectangle that's in the picture. But remember, we're not thinking about one rectangle, we're thinking about millions of rectangles. So each one has a force on it from the water. We have to add up all these forces. So when you add up all the forces, you get that the force, well, let's see, hydrostatic force, it's going to be sum. You have to add all these up. How many do we have? I know I said millions, but in general we call it n. So sum I equal 1 to n of rho g xi star 46 minus xi star delta x. And that's still an approximation, but it gets better and better when we increase the n. When we increase the n, two things happen. The rectangles look almost like the trapezoid, and the assumption that the depth at all points on the rectangle are the same is closer and closer to correct. Again, if you had millions of rectangles, the depth of the top and bottom of the rectangle will be almost exactly the same. So we need to send n to infinity to get the exact hydrostatic force. Limit as n goes to infinity. And so you know when you have a limit as n goes to infinity of a sum like this, this becomes an integral. It's going to be the integrals. Remember, this part becomes integral. Then this part becomes dx. And then you have to write all this stuff down, but instead of xi star, you're going to write x. It's going to be rho gx 46 minus x dx. Last part before we actually do the integral is, what are our integration numbers from? A lot of people get confused, but understand that it's basically where your rectangles are. Okay, so the integral is going to go from 0 to 16. If you think, oh, it should go to 20, I'm just going to say, well, this part of the dam has no water behind it, so there's not going to be a force there. So the only parts that give you a force are the parts of the dam where there's water behind it. So from here to here is the only part. So 0 to 16 is the only part. You could draw rectangles up here if you wanted, but there's no force on those rectangles. There's no water behind it. So it's integral from 0 to 16 of rho gx 46 minus x dx. Well, that's the hardest part of the problem. The rest of it is just to do this integral. So I'll go ahead and do the integral now. Okay, so the force is integral from 0 to 16 rho gx 46 minus x dx. Okay, so we'll do the integral. And don't let the rho and the g bother you. They're just numbers. I'm going to go ahead and distribute the x. So it's integral from 0 to 16 of rho g. And then we have 46x minus x squared dx. Now you integrate. When you have a number in the front, you can just copy it down. So rho and g will be copied down. And the antiderivative of 46x is 46x squared over 2. Antiderivative of x cubed, fx squared is x cubed over 3. And then you got to plug in 16 and 0. Let me simplify first before I plug in. So rho g. So it's going to be 46 divided by 2 is 23. So I have 23 x squared minus x cubed over 3. And again, we got to plug in 16 and 0. Look, when you plug in 16, you get rho g 23 16 squared minus 16 cubed over 3. When you plug in 0, you get rho g 23 times 0 squared minus 0 cubed over 3. You're going to get 0 for this term, but you don't always get 0 for that term, so make sure you plug in 0 and make sure you get 0. Okay, so we just get this first term here, rho g, and then if you multiply this out, you get, so it's 5888 minus 4096 over 3. If you get a common denominator in there, it's going to be 17664 over 3 minus 4096 over 3. So rho g, if you subtract these fractions, you get 13568 over 3. And then if you go ahead and plug in that rho is 1,000 and g is 9.8, and you multiply that with 13568 over 3, you get pretty big number here, 443 221 33.33, and this will be newtons. Yeah, so that's how that one goes. Let me go ahead and just do a little bit of erasing here, but that's how you do the integral. So I can write my final answer over here. So the force on that dam is, see where the commas go, 44,322,133.33 newtons, which is huge. That's why dams are made of really thick concrete, so that they can have this much force on them and still withstand it. And the book just goes ahead and writes this in scientific notation, just so you know. So they write the first three digits. They're at 4.43 times 10 to the 7 newtons, which is fine. But you could just write it like this. We don't have to worry about scientific notation. And that's example 1. Okay, so we'll go ahead and do example 2 from the book, so we can get a little more practice doing these kind of problems. Find the hydrostatic force on one end of a cylindrical drum with radius 3 feet if the drum is submerged in water 10 feet deep. Okay, so the first thing that's different between this problem and the last problem, there's not much that's different, but one thing that's different is this is in English units instead of metric system units. So we're not going to be using the rho, we're going to be using the delta instead. So we'll be using, when I use the force formula, we're going to be using the force formula that involves delta instead. Okay, next thing, I don't have a picture here, but let's try to understand what's going on as far as the picture goes. So they're saying the water is 10 feet deep. So if this is the floor and this is the surface of the water, this is 10 feet. And we have some kind of cylindrical drum submerged in there. So cylindrical drum, it says, has a radius of 3 feet. So 3 feet like this, 3 feet like this. So I guess my picture is not exactly to scale, and then it's 4 feet here, 4 feet to the top. Okay, so that's the idea. This is all water in here. And the cylindrical drum is submerged in there. And I'm just drawing the circular side of the drum. Side view of the circular drum would be something like this. Something like that. And we're just saying, well, there's water over here touching the drum, up here too, and all around it, of course. But if we just look over here, this water is touching the center of the drum. So it's applying a force this way on the drum, and our question is, what's the magnitude of that force? Okay, so my picture is not too bad, but I'd like to draw a little bit bigger. That's the bottom of the surface of the water there. Okay, and that's our cylindrical drum. And let's say this is the top of the surface of the water. Okay, so it's completely submerged in the water there. All right, so what we have to do first is we have to draw an x-axis. Now, where should we put the x-axis? Because there's a circle going on here, it's usually easy to have the origin in the center of the circle. because equations of circles become easier if the center is the origin. So I'm going to draw an x and y axis over here. Try to draw it so that it goes through the center. So this is the x-axis, and this is the y-axis here. And then the origin's in the center. That way, the equation of the circle is, when the center is at the origin, it's always x squared plus y squared equals the radius squared. They said the radius is 3, so that's the equation of the circle then, if you put the origin there. Okay, so we have our x and y axis set up over here. So the next thing is we need to cut it into pieces. Let's not forget the numbers that we have on our axis here. So this number here is 0 on the y-axis. This number here is 3. This number here would then be -3. And the distance from there to there is 6, and we know that the whole depth is 10, so this would be 7 over here. Okay, because remember, this distance from here to here is 10. But distance from here to here is 3. Distance from there to there is another 3. And so this has to be 4, so the total thing is 10. Okay, so we have those numbers. And where are we going to draw our little rectangles? Well, we're going to draw them only on the drum, because we're trying to find the force on the drum. And just, again, you have to imagine I'm drawing millions of rectangles. I'm not going to do one example where I draw, only 3 rectangles. Let's just draw one rectangle, but you have to imagine I really cut it into millions of rectangles. Our rectangles are going to be horizontal, and if I've drawn millions of rectangles, the width is so small that the depth at any point on the rectangle is about the same. Okay, so let's go ahead and draw a rectangle here. Let's go like that, and a little lower, like that. And there's our rectangle. It doesn't matter if either end touches the circle or some point in the middle touches the circle. When it's so small, that's like all ends are going to kind of touch the rectangle. Both ends of the rectangle are going to basically touch the circle the whole time because it's so thin. But I have to label some stuff, so we're going to label the coordinate of this point and the coordinate of this point something, and the coordinate of a point in the middle something else. So this point down here, let's go ahead and call it, well, it's on the y-axis, so I guess I need to call the top one y sub I. There's the bottom one is yi minus 1. And the middle one is yi star. That's the middle tick mark there. Okay, and the width of it, we'll call it delta y. We could have made that an x-axis, but just usually when it comes to writing equations of circles, we have the x-axis pointing left to right, the y-axis goes from down to up like that. So that means I'm going to just be using different letters. Okay. So now what do I need to do? I need to find the force on this rectangle, the hydrostatic force on this rectangle due to it being submerged in water. And then we'll add them all up for all the rectangles. And then, of course, we'll take the limit as n goes to infinity, because the more rectangles we use, the better approximation the rectangular area will be to the area of the circle. If you add all the rectangle areas up, it'll be a very close approximation to the area of the circle. And the assumption that the depth of the top, bottom, and middle of the rectangle is all about the same will be less of an assumption if we have such thin rectangles. Okay, so I have to take the limit as n goes to infinity. So first thing I need is the area of this rectangle here. I need to multiply it by stuff to get the force. So the force for this ith rectangle is, let's see, what was it? Instead of rho g dA, it was just delta dA. Where delta is the 62.5, d is the depth, and a is the area of the rectangle that I've drawn there. So it's going to be delta. What's the depth of this rectangle? How much below the surface is it? Well, let's be clear that the distance right here from the x-axis to the middle of the rectangle is that distance is yi star. But that's not the distance I want to know. I want to know how far below the surface the rectangle is. I want to know this distance. And I know the total of the the purple and the red is 7. So if this is yi star, this is 7 minus yi star. That gives me the depth of the ith rectangle. Okay, so 7 minus yi star. Okay. Then I need the area of the rectangle. Okay, so make sure you understood that 7 minus yi star, because I'm going to go ahead and erase that part. So how do I find the area of the rectangle? Well, you know it's going to be length times width again. So basically I need to know the length of it. The width we know is delta y. Right, so the width, this distance here, that's delta y. So we don't have a problem with that. I need to know the length though over here. How am I going to find the length? So length of this red segment, or the length of this red segment, or the length in the middle. Those are all the same thing. I need to find that length. Let's take a look at the length in the middle. And let me call half the length, so the distance from here to here, this distance, let me call that distance A for a moment. Well, there's not too much you need to do. You can just go ahead and draw a line like this. So you can draw a line like this and get a triangle going. The length of this purple part of the triangle, we already said that's yi star. The length of this is just the radius of the circle, that's 3. And this length here is A. So we can figure out A from Pythagorean theorem. It's A squared plus yi star squared equals 3 squared. Okay, and then we can solve that for A. So if you solve this for A, you get A equals, let's see, 9 minus yi star squared. Right, this is 9. You subtract over the yi star squared, you get A squared. So if you want A, you take the square root. Okay, so there's our A, but I need twice the distance. I need the distance all the way across. So I need 2A here. So the length of the rectangle, let's just call it L, is 2A. So it's 2 times this root, 9 minus yi star squared. So then over here, I'm going to be out of room, but to put the area of the rectangle, it's going to be the length, this, times the width, this. So it's times 2 square root of 9 minus yi star squared delta y. So that whole mess over there is the force on that rectangle. And you can just take a second to make sure that that formula works even if we're on this side over here. But it does make sense, because even if the y's are negative, and this distance over here, like if we have a yi star over here, this distance is not yi star, but it's a negative of yi star. If you square it, it's still going to be yi star. So everything's going to work out exactly the same. So because of the fact that we have a square here on the yi star, even if it's negative, it's going to work out fine. Okay, so now the last thing is, where are we going to integrate from? Well, we're going to have to integrate where the rectangles can go. The rectangles are basically supposed to cover the drum, so we're going to be integrating from -3 to 3. Okay, I mentioned all that because I need to erase the picture here. But just keep in mind that this Fi is the force on one rectangle if you cut it into a bunch of rectangles. So to find the total force, you have to add all the forces of all the rectangles. So the total force, well, you just have to add them all, sum I equal 1 to n if we have n of them. Let's see, delta 7 minus yi star, and then it's going to be times 2 square root of 9 minus yi star squared, and then delta y. And that's the force. That's the total force on all the rectangles. Remember though, I don't want the force on the rectangles, I want the force on the drum. So it becomes this force that I have written down here will become a better and better approximation the bigger n is, because again, the bigger n is, the closer the rectangle areas look to the actual circle area, and the closer my assumption, the less wrong I will be in the assumption of saying that the depth of every part of the rectangle is the same. So you do limit as n goes to infinity of this. And of course that means it's an integral, so it means the force is the integral. And we already said it was from -3 to 3. Remember, this part is the integral part. This part we're going to put dy, and then all this is going to go inside the integral, except instead of writing y star, you're just going to put y. And I'm going to take the 2 in the delta and put it in the front. So 2 delta, and then it's going to be 7 minus y, and then square root of 9 minus y squared dy. Okay, so that's how you set up the integral. And of course, once you set up the integral, then you just do the integral. Okay, so we'll do the integral on the next slide. Okay, so the force is the integral from -3 to 3 of 2 delta 7 minus y square root of 9 minus y squared dy. Okay, well, how are you going to do this integral? Not the easiest integral the way it stands, but if we multiply things out a little bit, it will become a little bit easier. You can write this as the integral from -3 to 3. The 2 delta is not a big deal. Maybe I should just put that in the front. Remember, in the front, you just copy it down, or I could pull it out of the integral. So, and then I'm going to distribute this. I'm going to do 7 times the root, and then minus y times the root. So we get 7 times square root of 9 minus y squared dy plus, and then the other integral. Instead of using parentheses, I'll just write the 2 delta again. 2 delta integral from -3 to 3 of, oh, it's a minus, isn't it? Okay, I'll fix that after. So y square root of 9 minus y squared dy. Minus like that. So basically we have to do 2 integrals. Okay, so let's work on each of these integrals. So integral 1, I won't copy down the 2 delta, let's just copy down the rest. Actually, I don't even have to copy down the 7, I suppose. But okay, let's go ahead and leave it for now. So I guess this is a trig sub. So let's let y equal 3 sine theta. That makes dy 3 cosine theta d theta. And the integral becomes 7 square root of 9 minus 3 sine theta squared. And dy is 3 cosine theta d theta. Now you could change the numbers if you want, or you could leave them alone. That's up to you. You can leave them as -3 and 3, but you don't plug -3 and 3 in for theta, so you have to figure out what the new numbers are. If you wanted to change the numbers, this is what you would do. You realize these numbers belong to y, since it's a y integral. So you plug in 3 there, figure out what theta is. Plug in -3 there, figure out what theta is. Actually, why don't we go ahead and do that? So real quick, if I plug in 3 for y, I get 3 equals 3 sine theta. And that gives me theta, gives me sine theta equals 1. And so we have theta equals pi over 2. If you plug in -3, you get sine theta equal -1, and that means theta is negative pi over 2. If you're wondering where I'm getting these numbers, you have to think, what is the angle where sine is 1? What is the angle where sine is -1? There's lots of angles that do that, but when you're dealing with trig sub, we need to be thinking about the inverse function as well. So there's sine and then there's inverse sine. And when it comes to inverse sine, the answers are always between negative pi over 2 and pi over 2. So every time you're finding an angle, your answer needs to be between negative pi over 2 and pi over 2. So even though there's plenty of angles where sine is 1, this is the one we need. Okay, sine is 1 at theta pi over 2 and other ones, but the only angle between negative pi over 2 and pi over 2 where sine is 1 is this angle. Same thing here. The only angle between negative pi over 2 and pi over 2 where sine is -1 is this angle. Again, you don't have to change the angles, but change the numbers, but let's just go ahead and go through it. So that's how you do that. So this would be negative pi over 2 and pi over 2. Okay, let's see where we're at. So we have integral from negative pi over 2 to pi over 2. Okay, 7. And inside here we have, so it's 9 minus 9 sine squared. If you factor out the 9, we got a 1 minus sine squared. And then a 3 cosine theta d theta. And we know that that's going to be a cosine squared. Square root of that is going to just give you cosine. So we have integral from negative pi over 2 to pi over 2. So 7, and then 3 cosine theta. And then, so this is going to give me a 3 cosine theta, and then we have another 3 cosine theta outside. So we have integral from negative pi over 2 to pi over 2 of 63 cosine square theta d theta. Okay, out of room. So let's erase some stuff. So we're at this step here, negative pi over 2 to pi over 2 of 63 cosine square theta d theta. Now you know when you integrate cosine squared, you're going to be using the half angle identity. This is going to be integral from negative pi over 2 to pi over 2. So 63, and this is 1 plus cosine 2 theta all over 2 d theta. So we're going to have 63 over 2, and then you have to integrate 1 plus cosine 2 theta. So now we can integrate, so you copy the number down, 63 over 2, and then theta plus sine 2 theta over 2. And you have to plug in these angles. When you plug in pi over 2, you get 63 over 2, pi over 2, plus sine. If you plug in pi over 2 in there, it's going to be sine of pi, and then all over 2. And then when you plug in negative pi over 2, negative pi over 2 plus sine of negative pi all over 2. Once again, out of room, so we'll erase some more stuff. But we're almost done with this integral. Sine of pi is 0. Sine of negative pi is also 0. So we just get the 63 over 2 times pi over 2. The other term is 0 in that parentheses. Minus 63 over 2, and then a negative pi over 2. And these negatives cancel. So we get 63 over 2 pi over 2 plus another 63 over 2 times pi over 2. And that's going to be 63 over 2. Think of factoring out the 63 over 2, and then you get pi over 2 plus pi over 2, which is pi. So we get 63 over 2 times pi for that integral. Okay, so we just figured out this right here is 63 over 2 pi. All right. And now we'll work on the second integral. So the second integral, there's a couple of ways to do it. The book mentions a way that makes it real easy to be done in a couple seconds if you understand what they're saying. So integral 2. So integral from negative 3 to 3 of y square root of 9 minus y squared dy. So here's what the book says. The book says that the thing we're integrating is an odd function. And when you integrate an odd function from negative 3 to 3, well, what I need is that one of these numbers is these numbers have to match exactly, except one is negative, one is positive. Okay, so negative 3 to 3, negative 5 to 5, negative 12 to 12, that kind of thing. Then if you integrate an odd function, you get 0. What do I mean? So here's what I mean. So an odd function, let me just draw an example of an odd function. Something like this. Actually, that's really bad. Let me try again. So there's an odd function, and if you were integrating from negative 3 to 3, let's say negative 3 was here, and positive 3 was here. Oops. Okay, positive 3 there. Well, the integral from 0 to 3, okay, from 0 to 3 would be this area here. The integral from negative 3 to 0 would be this area, except the second area I'm drawing, because the curve is below the x-axis, would be counted as a negative. Otherwise, those areas should match. I mean, I didn't draw the best picture in the world, but these two areas should match. So in other words, if this area is 5, this area should also be 5. But when you do an integral, when you do the integral, you'll get the area here because the curve's above the x-axis, but you get the negative of the area here. So long story short, this part of the integral would give you something like positive 5. This part of the integral would give you something like negative 5. So you get 5 plus negative 5, and you get 0. So it has to be integral from negative 3 to 3, and it has to be an odd function. So now how do I know that's an odd function? Well, the way you check algebraically without drawing the graph that something's an odd function is you replace all the, like if it was an x, you would change all the x to negative x and see if you get the negative of the original function. So the definition of odd function is that f of negative x equals negative f of x. What that means is change all the x's in your formula to negative x, simplify, and if you get the negative of the original formula, then it's odd. Of course, it's y instead of x here, so you would do f of negative y. So you have to change every y you see here to negative y. So you get negative y square root of 9 minus negative y squared. If you simplify, the only simplifying that really happens is the inside. The negative gets squared. You get 9 minus y squared. And you see that other than the negative sign in the front, the rest is the original function. So you get the negative of the original function. That makes it odd. So since it's odd and we're integrating from -3 to 3, we know the answer is 0. So right now I know that integral is 0. Now, of course, what if it wasn't from -3 to 3? What if it was from -3 to 1 or something? Then you'd have to do the integral. So let's go ahead and just do the integral anyway. And also that way we'll be able to see that we get a 0 answer. So now doing the integral, other than using this little trick, which is a nice thing to know because it saves you some time. Sometimes it will save you some time. Okay, so this is the integral we're trying to do. Well, it's going to be a u sub because the derivative of the inside of the root is essentially the outside of the root. So u sub, you're going to make u equal 9 minus y squared. That makes du -2y dy. If you divide by -2, you get y dy equals -1/2 du. And then the integral becomes the y dy, that's this, becomes -1/2 du. So I'll put a -1/2 du out here. And it's going to be square root of u. And while we're at it, might as well change the numbers. Remember, this number and this number belong to y, but I want to know what the u number is. So you plug both of these numbers in for y there, and you figure out what u is. So when you plug in the -3 here, you get 0. When you plug in +3, you also get 0. So you integral from 0 to 0, which is fine. And also, when the integral starts and ends at the same number, you get 0. So integral from negative, so if you did an integral from like 5 to 5 of stuff, the answer is going to be 0. Or if it was 8 to 8, well, as long as the two numbers are exactly the same, you get 0. Since these numbers are exactly the same, once again, I'm supposed to get 0. So anyway, so we can see from there the answer is 0. If you're still not satisfied, the answer is 0, then we can just do the integral. So we're doing the integral from 0 to 0 of -1/2 u to the 1/2 du. You find the antiderivative, you get -1/2 u to the 3/2 over 3/2. Plug in 0 and 0. And you get, if you flip the 3/2, it's 2/3. You get -1/3 when you simplify u to the 3/2. Plug in 0 and 0. So you get -1/3 times 0 to the 3/2 minus -1/3 times 0 to 3/2. Anyway, you get 0 minus 0, you get 0. So somehow or other, a lot of ways to see it, the last integral is 0 there. Okay, we're almost done with getting the answer here. So now what we're going to do is just go ahead and just plug in the answer so we can get the final decimal answer going over here. So now it's 2 delta. Don't forget delta was 62.5. And that integral was 63 over 2 pi. And then minus 0. The other one was 2 delta times 0. So you can go ahead and calculate what this is. I'm getting 12,370. I'll just go ahead and write down all the decimals just so you can check it with your calculator, but you can round a little. I mean, that's a little crazy how many decimals I'm putting here. And then, of course, since this is in English units, this is going to be pounds. So that's how much force this cylindrical drum is going to feel. And that is the end of this example and the end of the video. So, guys, study hard. I'll see you next time.